Okay, now we'll talk a little bit about wave speed and how fast the wave moves, or how fast the energy in the wave moves. In general, speed can be found from distance traveled over time. So in a wave, that's going to be the wavelength, how far that travels in a period of the particular wave. Since wavelength and frequency are inversely related, we can say the speed is equal to the wavelength times the frequency. It's most commonly how it's written. This is known as the wave equation. Again, it's speed, the velocity of the wave, is the frequency, how often it vibrates, and usually in hertz, and the wavelength is the distance from crest to crest or trough to trough, etc., in meters. The speed of a wave refers to how far it's going to travel. Any one point on the wave is going to travel per unit of time. We can find that from V equals frequency times wavelength, lambda, or we could find it from lambda over the period. Symbol for period is capital T. So meters per second, 1 over seconds, seconds to the minus 1 times meters, both would give us meters to the minus 1. Meters per second to the minus 1. A couple of people, Macintosh, are resting on top of the water, and they create waves, and they see it travels the length of the pool and back in 25 seconds. The pool is 25 meters long. Determine the speed of the wave. Now, you have to be careful. It's to the length of the pool and back. So it's traveling 25 meters of distance in 1/2 of 25 seconds, because it's going to go the full length of the pool in half of that time. So that's going to make it 25 divided by 12.5, which is essentially 2 meters per second. So that's 2 meters of distance moved every second that it travels, or 2 meters second minus 1. And that is the speed of the wave. Sonic rangers are used, sonar, used to find depths all the time. Sound travels about 1,210 meters per second through the water. It travels faster in water than it does in air. And it requires 0.02 seconds to travel to the lake's bottom and back to the boat. How deep is the lake? Well, that means I'm actually looking for the length of how far the object is. So I'm looking for the distance. And distance is going to be speed times time, the time it took to get there. So that's 1,210 meters per second times, now again, it's 0.02 seconds to go to the lake bottom and back. So I'm going to want to divide the 1,210 not by 0.02, but by 1/2 of 0.02, which is 0.01. Which is going to give us a depth of just about 12 meters in this particular location. Now, of course, the actual speed of sound changes based on temperature and other effects. So this may or may not be accurate, but at least gives us some idea of how deep the lake is. Okay, so now we do the same kind of thing, but with some pictures. We have a wave that's traveling at 3 meters per second. That's hitting Wilbert's perch over there. Wilbert's the bird. 6 meters is the distance between crests, so 6 meters is going to be your wavelength. This is your velocity. It wants to know how much time passes between each successive hit of the water, with thus drenching the bird's feet. So we can find the speed of a wave by taking the wavelength divided by the time. Therefore, we can figure out the period by taking the wavelength divided by the speed. That's 6 meters over 3 meters per second. That means the period is going to be 2 seconds of time. So every 2 seconds, a crest is going to hit the perch, and that's going to cause Wilbur's feet to be drenched. Slinkies are one of the things we're going to be experimenting with. These people did a little experiment, and they changed wavelengths and frequencies and looked at different kinds of coils and changed the material that the coils of springs were made of and the size of the springs, and they got these various different things. We can calculate the speed v by using the wave equation, which is simply the wavelength times the frequency, or frequency times the wavelength, and 1.75 times 2 is going to be 3.5 meters per second. These are all going to be in meters per second. 0.9 times 3.9 is 3.5. 1.19 times 2.1 is going to be 2.5. 0.6 times 4.2 is going to also be 2.5 to two significant figures. 1.82 times 2.2 is going to be 4. And 0.95 times 4.2 is going to be also 4 to two significant figures. Now notice that when the material and the size of the coils were the same, changing the wavelength adjusted the frequency, but it did not change the speed. So speed is dependent upon the material that the wave is moving through. So the speed of sound in air is different than the speed of sound in water, is different than the speed of sound in steel, is different than the speed of sound in copper. So wave speed is mostly dependent upon, especially for mechanical waves, what we're talking about, is dependent upon the material that you're trying to move the wave through. It's not dependent on the various wavelength and frequency. If you increase the wavelength, what's going to happen is the frequency is going to have to decrease to get you back to that set speed. So as you increase the frequency in a wave, you're going to find that you're going to so here's a wavelength wave moving. Now if I adjust the frequency of the oscillations, let's make them slower, you should notice that as I reduce the frequency, the wavelength becomes much longer. Look at all those short wavelengths to the right, look at the long wavelengths to the left. So, but the speed at which it moves down that particular spring or string is going to be basically the same. So as the wavelength of a wave in a uniform medium, the same stuff, as the wavelength increases, the speed remains the same. If the stuff is the same, the speed will be the same. As the wavelength increases, then the frequency is going to decrease for the same medium. That's the only way we can keep the speed the same. So the speed of a wave actually depends upon the properties of the medium through which the wave travels. So again, sound travels different speeds in different properties, different materials. Okay, we'll wrap it up here with the water gun fires 5 squirts per second. The speed of the squirts are 15 meters per second. How much distance is there between each consecutive squirt? Think of the water as being maybe the crest of the wave. If you want to think of it in terms of waves, we have 5 cycles or 5 squirts of water per second. So the frequency is 5 hertz. And the speed is 15 meters per second. So if we're looking for the wavelength, again, the speed is equal to the wavelength times the frequency. So therefore the wavelength is equal to the speed divided by the frequency. So that's going to be 15 meters per second divided by 5 hertz. That's 3 meters for this particular in between length of the squirts. If we were to increase the rate of fire, to fire more often, then there would be less time between each shot. That would make the frequency would be increasing as the period went down, and if the frequency increases, then the wavelength, the distance between crests, is going to go down. So we'd see less distance in between each squirt. Again, it's analogous if you think of it as each squirt being, say, the peak of the wave, then the same exact thing happens within waves. As you increase the frequency, you're going to have to decrease the distance between each wave, crest or trough, or any two like points. All right, well, that's all the basics of the fundamentals of wave properties and some of the key terminology you're going to need to use as we study simple harmonic motion and wave forms.